This is lecture 21, a continuation of friction. This is actually the third lecture on friction, and we'll have one more, the fourth. But in this lecture, I wanted to talk about the concept of wedges. So up to this time, or up to this point, what we've discussed is basic friction and how to do calculations of moving object, or not moving objects, it's objects that are impending motion. So up to this point, we've always assumed that the object is on the verge of slipping or sliding. And when you get to next quarter in dynamics, if you take dynamics, then you'll see this continuation of friction, only it'll be dealing with motion, bodies in motion. So anyway, let's talk about wedges though, because they're kind of a unique subset of friction. Now, most of you are familiar with wedges. You use them to hold your door open, and the idea though, the basic concept of a wedge is the fact that you have a extremely large normal force that is created by applying a relatively small lateral force. So I guess the best way to describe this is if you think of trying to split wood. So on the right, I have this picture of a modified wood grenade, they call it, and when you put it in the middle of the wood and you strike it with a hammer above, the forces that are created in the outward direction to split the log are much greater than the force of input from P. Now, that's one example of the wedge, but what we're going to look at, not so much as the way that this creates this large force, but what we're going to do is we're going to look at it as how it actually magnifies the friction force. And it magnifies the friction force by a combination of how big the wedge angle is and how much the coefficient of friction is. So for example, let's first talk about this concept of what's called an angle of repose. Now, you saw this in your book if you've been reading it diligently. And let's go through these figures and then I'll switch to camera mode and we'll talk about this sketching things out. So what you have is in the first picture, you have no friction. So that's because you just have a force from above. So there's no right to left force. So nothing happens. Your normal force equals your weight. Now, plus whatever applied P you have. Then if you think about the next image, you have a slight force P in the X direction. This is in B, but you haven't applied enough force to get the object to move. And then you have in C, you've put enough lateral force so that now your force is great enough that it's going to cause motion. And then in the final one, you've exceeded the friction force and now you have motion. But what you're probably not sure about are what are these angles at the bottom here. And so what those represent is the angle of friction. And the angle of friction can be related to simply by looking at the geometry of the actual resultant force. So what I want to do is explain that on paper because I think it's a little easier. In the classroom, I draw diagrams, but here we have to do it this way. So let me go ahead, stop share. So here we have our box, and let's say we apply a load P going that direction. Now, what we've talked about so far is that the friction consists of A, generally drawn as a vector going opposite direction, so going to the left, and you have a normal force going up. Now, normally those are the only two things that are there. If we cover up R, then all we have is the normal force and the friction force. But you see how there's a relationship here. The friction force is perpendicular to the normal force. So if we add the friction force and the normal force, we get what's called R, or resultant force. And that resultant force is just the combination of those two vectors. Now, if we want to know what the angle is here, then the angle is going to be, as in any right triangle, it's going to be the tangent of this angle. We'll call this angle phi, angle of repose. So tangent of phi is equal to the the ratio of the friction force over the normal force. Now, where have we seen that before? Well, we know the friction force over the normal force is also mu static, right? So really what we can say is the tangent of phi is equal to mu static. So if we want to know what this angle is and we're given the friction force, then all we have to do is take the inverse tangent of the friction coefficient, not force, I'm sorry, friction coefficient, and that will give us our angle. So what does that do for us though, you ask? Because before we were fine doing this and this, but now we have this angle. How does that help us? Well, before we jump in that, let's look a little bit more about the limitations of this. Now, in friction, as I discussed in the first few lectures, is the coefficient of friction being the ratio of this to this is generally a number between 0 and 1. And in our universe, we're going to stick to that. It is possible to have a friction coefficient greater than 1, but that's in vacuum and highly specialized situations that aren't really practical and the laws kind of break down. So we'll stick from 0 to 1. Now, we also know that if the friction force is equal to the normal force, then that tells us it's the same as 1, isn't it? So if we know that friction force over normal force, if that equals 1, then basically these two are the same. But we also know that if we take the tangent of 45 degrees, that's also equal to 1, isn't it? So this angle of friction, the greatest it can be is 45 degrees, because anything past that is going to exceed this 1 value. So we never have situations in this class where it's going to occur, but you're always going to see this angle is going to be somewhere between a very small number and 1, or 0 to 45 degrees. And so we can think of it as, if we were to draw this at 45, then just like this, that's friction, that's normal, and that's 45, then tangent 45 is 1. Or if mu static equals 1, then we get 45 degrees. All right, so I don't want to belabor the point, but that is the concept. Now, how does that matter and why do we care? So one of the things that we can think about is when we talk about a wedge. Now, I've said what a wedge is, but really when we think of a wedge, we think of something that looks like this. So we apply a force P, and what I was saying is you get a huge force going out this way, this normal force. This normal force is much greater than P due to the geometry of this wedge. But you also have a friction force that's going to offset. So when you're trying to pound P into a block, there's friction force that's restricting it. And that's why that friction force is what actually causes the wedge to become embedded. It's the same idea if you pound a nail in. It's the friction force that's keeping the nail in the wood. So how this relates to our concept with wedges is if we were to then, let's say we just take a half wedge, or the wedges that we're mostly dealing with look like this. Okay, so there's our wedge. So now we have our wedge, and let's imagine that we apply our load P over here. So let's say that our wedge, we'll just give it an angle. We'll say that that's theta, and we'll say that theta equals 10 degrees. All right. Now, we're also given that this wedge, let's say that it's on the ground. Okay. So it's on the ground, and we also know that there's some kind of like object up here. So let's say this is the door. This could be like a door stop. All right. So here's the door stop. Here's the door. You're pushing it in, and this is that Ignore the fact that this is deforming and it's a rubber and it's made of rubber, just to pretend that that's at the same angle there too. So what we have then is we have this surface, we have this surface, and we have the P. So let's say that we say that mu static is equal to 0.3. So if that's the case, then if we take the inverse tangent of 0.3, then, so if we take tangent minus 1 of 0.3, that gives us basically 16.7. All right, so just check that again. Yeah, so 16.7 degrees. All right, so what does that mean? So if we redraw this, let's redraw this as a free body diagram. And so we have P here. Now, let's say we want to figure out what the reactions are. Well, at the bottom here, we know that we can draw this reaction we'll call R1. And this angle here is going to be our angle of repose, right? Just like in the block we showed before earlier, you know, irrespective of being a wedge, the fact that we're trying to push it this way, if we combine the friction force and the normal force, we get this R1. So this angle here has to be phi, which is 16.7. So we know this is 16.7 degrees. Now, the same idea holds true up here, but the fact is that this wedge also has an angle. So if we draw first a vertical line, and then we draw a line like that, so this represents the 10 degrees. Now we add to that the R, and this represents phi. So because we have the wedge now, R, this total angle between the resultant and the vertical, is 10 plus 16.7, or 26.7 degrees. So effectively, if we take 26.7 and we take the tangent of it, that is the equivalent of mu static equal to 0.5. So what we've done is by adding this angle here, we've increased the friction coefficient there. Now, of course, there's practical limits to it. That's why wedges are always very small angle-wise, but you can see what that has done. Now, to solve this, if, for example, we knew what this force was coming down, then we could solve it by simply summing the forces in the X and summing the forces in the Y, or we could create a force triangle. And that's actually the first example we're going to do, is solving using a wedge. So go ahead and share screen again. There we go. So here's our example. So, and this is right off the worksheet. So here we have something similar. We have the wedge down here. It's a 10-degree wedge. And then we have a 600 Newton force applied here. So as we can imagine, if we apply a force here, it's going to push down here. And what we want to know is, given that force, how much effort or force P do we need in order to move that to the left? So if we move it to the left, it's going to require a certain amount. So let's look at that. How are we going to do it? So what I would recommend is, given what you know, go ahead and try this problem yourself. Use what I've shown you. Now you're going to have to sum the moments about B, which is fairly easy. You know that 600 times 200 is going to be the same as whatever this reaction is times 250. And then you have to account for the angle. and then you have to account for what's at D. So I would suggest try the problem, work it out, see how far you get, and then come back. Okay, so you're back. And what was only a second for me may have been 20 minutes for you, but here we are. So let's go ahead and look at what we have. So we have 600 newtons. Now, I've drawn it. This is A up here, and there's C down here. So I know that's 0.2, that's 0.25 in terms of distance. I have 600 there. All right, so now what I've done is I've taken the wedge and I've kind of drawn it, I've magnified it. And I've also drawn what this surface looks like here. So really what I want to know is what is this value here? This value and that value are going to be exactly the same. They're just equal and opposite pieces. So let's first look at what this value is. So we'll call this, I'll call this R reaction C, and let's call this reaction C. Now, if we want to figure that out, we know that for one is if we sum the moments, move this up just temporarily, sum the moments at B to 0, we know that negative 600 times 0.2 plus RC times 0.25. Now, RC is not the vertical component. So we need to know that's the vertical component. So in order to know RC, we're only getting part of it. So cosine of what? Now we have to think of what is this angle. So if we think about this angle here, it's the same as this angle here, right? So it's going to be the cosine of 10 degrees, because that's your wedge, plus, remember that this is 0.2, 11.31, so 11.31 degrees. Okay, so if we solve for that, we get RC equal to a value of 515 newtons. So hopefully you understand that. If you think about, if you look at this component here, this is the straight down force. So we could have solved for that directly. If we had done that, then that would have given us a value of 4. Yeah, so this value here is about 480 roughly. And then, of course, we know that 480 divided by cosine of this whole angle, this is RC. So that's where that came from. So the main point is to understand is that we sum the moments, we want to get RC, got that. All right. So now that we have that, we can pretty much solve the problem because we're trying to find this value P. Now we also have this RD down here, which is the friction against the ground, but we really don't care about that much. Now that again, that angle is going to be 11.31 because it's based just on the friction coefficient. Whereas this angle up here is 10 degrees plus the friction coefficient. All right. Now you could, as you can see, you could sum the forces in the y direction. If you did that, it would basically be RC cosine this negative, or just set them equal. RC cosine this equals RD cosine that. You get RD, and then you take RC sine of that plus RD sine of that equals P. So that's one way to do it. That's fairly straightforward. Another way to do it is with the 11-fourth triangle. And so if we were to do it that way, what we would get is something like this. Now remember, with the fourth triangle, we always draw it based on the geometry of what we have. So we know that P is going this way, and we know that RD goes up like this, and RC comes down like that, right? So there's RC, P. Okay, so now what are our angles? Well, we know RC with respect to vertical, that angle there is going to be 11.31 plus 10. And we know RD is just going to be 11.31, right? So this angle here is just the friction angle, B. That's B plus 10, okay? Sorry, it's kind of a little bit out of focus. So then we know this angle here is just going to be 90 minus that. So that's just 90 minus 21.31. And this angle here is just 90 minus 11.3. And there we have it. So we want P, right? So we know that law of sines, P over the sine of, which is 22.62, so 32.62 has to equal RC divided by the sine of 90 minus 11.31. All right, so if we do that, we get a value of 283 newtons. So P equals 283 newtons. And that's what we get. Okay. Now, part of this question, the second part of this question has to be to find what happens if you want to move the wedge the opposite way. And though the calculation's easy, the concept's kind of interesting because now it shows you how the wedge works for you to actually reduce the friction. So what do we mean by that? So if we go back up here, let's go ahead and redraw this. So now I've redrawn it. So here we have P. Now we're going the other way. And we have RD is switched. Now it's still on a flat surface, so nothing's changed. It's still going to be angle of repose, or P equals 11.31 degrees. Now what's interesting about this side is RC. I haven't drawn it in here. What I did is I drew the normal to the wedge and the straight up and down line. So we know that's 10 degrees. Now remember that we measure our friction force from the normal to the wedge. So we actually measure from here. So we go here out and we only go 11.31, but we're already 10 degrees going that way. So now what we end up with is this little tiny sliver, hard to draw. That's my RC. And so my effective angle is only 1.31, right? 11.31 minus 10. So this whole angle from here to here is 11.31. So that little bit is 10.31. So that will, of course, make sense intuitively that it's much easier to push the wedge away from the door because the material will be falling away. So, of course, the friction's going to disappear. But we're just talking about that instant when it starts to move, because then, of course, contact will disappear. But so if we look at that again and we put it in our forced triangle, I've just reversed. I have RD on this side, RC on that side. And now the normal RD side, 11.31, 90 minus 11.31. But now this is only 1.31 degrees, which then makes this down here, what, essentially 88.69. So this ends up being 88.69 degrees. So if we do, again, P over sine of 12.62, which is just these two added. Sorry, up there. That 12.62 is those. That has to equal RC over this opposite, which again is just going to the RC value itself hasn't changed. It's just the effect on P is not changed. So that's going to be sine of 90 minus 11.31, which was what, 78.69 degrees. And so if we plug in our RC, then we still have the same value. And the difference now is we end up with a much smaller P. Now, before I plug it in, I want to point one thing out, that we are decreasing RC also. So now RC is no longer 515 because of this fact that this reduced to 1.31. We have to redo our moment equation. I should have done it sooner, but remember that we took the moment about B to 0. What do we get? We had the 600 times, well, actually, we don't even need to do that because we know that, remember I said, if we go back to this, we know that this vertical part's 480. So if we take 480 and in order to get RC before, we divided it. So 480, sorry, it's getting a little messy, but 480 divided by the cosine of 21.31 degrees. That's what gave us the speed value 515. But if we take 480 and we divide it by the cosine of just 1.31 degrees, which is what it would look like the new one, this gives us a value of 480.1. That's it, very little difference. And that again is because of this wedge angle going from effectively 21.31 to effectively 1.31. Okay, sorry about that. That's not straightforward. We'll do more of these, so hopefully come back. Now, so if we put in 480.1 for this, we end up with P being a fairly small number. P ends up being 107.0 newtons. There we have our answer. Okay. So that's the first example. I hope that made sense. Again, the main takeaway points from this are that you have to account for that friction angle here. And once you figure that out, then if you prefer just some forces in the X and then some in the Y, that might be easier for some of you. I prefer the force triangle, but again, feel free to do it either way. I would rework this problem if I were you, just make sure you understand, see where everything went. If you have questions, of course, ask me off hour, but I'm also going to do other examples. So getting back to that. Go ahead. Yeah. All right. So this problem here is another example of how wedges work. All right, this next example, we have a 1,400-pound statue base, and we're trying to drive a wedge under one side of it. And so we're given that the wedge is 5 degrees, and the total weight is 1,400 pounds at the center of gravity, which is G. So we know that from A, 50 inches over, there's G. So it's not going to be symmetric in terms of its weight. So we're given the friction coefficient is 0.2, and we want to know what the force P required is to move the wedge. And then we also want to know whether the machine base will move with the wedge. So that means essentially is if we move P, we try to essentially move the wedge in. Is the friction at B going to be great enough to prevent that, or is the whole thing just going to slide instead? All right. So first thing we want to do is figure out what are the reactions at A and B. And so what we can do is we can first look at a 3-by diagram. So if we draw the reactions, we have AX, AY, BX, BY, we have G. All right. Now I've drawn the reactions, and they're AX and BX can also be looked at as the friction force. So that's another way. In fact, if it's easier, we can think of that is, the force that we're putting on AX and BX. I can think of this as our force P, and we'll just leave this as BX. Actually, that's probably better. But let's first figure out what the AY and BY are. So we know that if we sum the forces at one of these points, if we sum it at A, then we can solve for B, or B and solve for A. So we've done that before. You don't need to rehash that. So if we do that, we find out that there's 400 pounds at A and 1,000 pounds at B due to the mismatch in G. So we know that now. So now what we're going to do is we're just going to look at the wedge. So we want to look at just this side here. And let's look at that. Now we also knew that friction was 0.2, which equates to a angle of 11.31. So if I go ahead and I draw my wedge looks like this. I have P going that way. And as usual, we know we have, there's my reaction here. Let's just call that, we just call it R1. And we know that we have one that is up here. Now, remember that this is just going to be the angle of friction, right? Just like before, 11.31 degrees. This here is going to be the wedge angle plus the angle of friction. So we get 16.31 degrees. All right. So we can call that R2. So we have those. Now, what we want to do is, again, we want to figure out what is what in terms of the friction and what is the load. Now, this one's a little is interesting because if we look at this again, we look at AY. We know we have a vertical force there that's 400 pounds. So if we draw our force triangle, it looks kind of like this. Again, it doesn't matter which P on the top of the box. So there's P. And then I know that I have, and I'll move my paper in a second. So I know I have P. Now, what I want to do is I also want to draw this vertical one, which might be, so we have P, and we have these two angles. Now we know this angle here is 5 degrees. And we know this angle here, though it doesn't show it from my drawing, this is actually going to be 11, no, I'm sorry, you know what I did? Yeah, 16.3, sorry about that. Yeah, this is 16.3 degrees. So yeah, so 16.31 degrees, all right. And so there's 5 degrees, 16.3, sorry for the total mismatch in ratio. So we know that in this case, that this one over here, this is going to be my R1, this is the R2 value. But again, we don't really care about those per se. What we want is this. But notice how we have a vertical force in this triangle, a vertical component of this. So if we were to separate this triangle, what would we have? We would have the vertical component and the friction component. And that would be that, wouldn't it? So that's the 400, and then the friction component, and that would give us my R2. So because of that, we know the 400, then we can use that relationship of these two right triangles to basically solve for P. We know that P is going to be a combination of this friction here from the wedge top and this portion here from the wedge bottom. All right. So so it should actually look the opposite. This should be the 16.3 bigger, but You get the picture. So if ignoring the physical discrepancy in my triangle, each of these pieces consists of p. So what we end up with is just p equals 400, and then tangent 5 degrees, because that's going to give you that opposite component, and then plus 400 tangent of 16.3 degrees. Or I could have just done tangents of 21. Either way, it would have been 197.0 pounds. Okay, so that tells me that based on the friction, at this point here, it's going to take me 197 pounds to drive that wedge under that point there, given that there's 400 pounds there. All right. So now we have to look at, well, we still have, there's still this wheel here that's holding it back. And we can't neglect the fact that this isn't going to, the whole thing isn't going to want to move. So if we think about the total coefficient of friction, I'm sorry, the total friction force, what is that going to be? Well, the normal force here is what? It's 1,400 pounds. And so the friction force total is going to be 0.2 of 1,400. And so that gives me a value of 280 pounds. So 280 pounds is how much force I'd have to exert in order to move that block. And that's only 197. So as a result, it doesn't move. Now, if I had done the same problem the other way, going from this end, then what I would have found is the force required to move underneath here would have been greater than that. And so it would have actually slid before it went. Now, the only difference between driving the wedge on this side versus that side calculation-wise is you would have replaced this vertical value with 1,000. So if you did P equals 1,000 times tangent of 21.31 degrees, then you would have got 493 pounds. So that means you take 493 pounds to drive the wedge under this end. And so it'd be too much and it would just slide. Okay. So I hope that wasn't too strange. Another way to kind of, like I said, look at it is, if you think about it, if you look at the wedge, you have 400 pounds is your vertical, right? That means you have 80 pounds of friction force there because of that angle of 0.31. And up here you have 400, and then you'd have whatever that respective amount is, tangent of 16.31. So this 80 is basically tangent of 11.31. And so since we found it was what, 197, so if that's 80, then this would have been what, 197, this would have been 117. There we go. So this side would have been 100. So effectively, you would have found 117 pounds of friction from this side of the wedge, 80 pounds from that side of the wedge. That would have given you that P value. If that helps understand it. All right. Good. So what we have with this. So this one is very similar. And given time, I think I might skip this one for now, but this one, it requires several steps, and it's probably beyond what you guys will need to know for the final. So I may or may not post the solutions if I think they're important for the final, because I don't want to overwhelm you guys, but most likely you're not going to see anything like this. So given that I've been talking for quite some time, I want to not exacerbate this or make this lecture too long. So let's go ahead. Let's talk about screws briefly. And these are another interesting concept. And I don't plan on, if there is anything on the final, it'd be minimal on this. But the idea with screws is that they are inclined planes, and they represent friction inclined planes. So just like we talked about wedges as a inclined plane that has friction on it, you can think of a screw as something that has just a continuous wedge that just goes and goes forever. So if you were to actually unwind a wedge, you would have one full circle of the wedge would be equal to the circumference of the circle. Now, fasteners are interesting beyond the scope of this class, but they're something you should understand. You probably will come across them depending on what you do after you're out of school. But you can think of most common things when you think of fasteners are the pitch and the diameter. So for example, like a 1/4-20, that's the size of the hole in the bottom of cameras. That's the standard. So if you have a tripod and you mount your camera or even your video recorder, you're going to use a 1/4-20. So the quarter is just that's the diameter. That would be the major diameter. And the 20 is going to be the threads per inch. And so there's also 1/4-20, I think 26, and that would be a finer thread. But anyway, that's the idea with threads. Now, how do they actually work with friction? So it turns out that with screws, you can model one full rotation as a wedge. So this example here, you have Q and W. Now, what do Q and W represent? I may have to go back to the previous slide. No, maybe not. Q represents the force that you're imparting. So if you imagine if you're trying to rotate a screw or turn a screw with a wrench, the Q value is going to be the force that you're applying to the nut to make it screw onto the bolt. The W force is going to be the force that is applied from as you compress the nut to the screw. I think I said that correctly. So what you have in this case is if you're trying to tighten a screw, you have impending motion. So you have a certain applied force. You're trying to push the wedge up the hill. And in this case, the block is modeled as the threads, which were in contact all the way, but we just use a block for it. And you can see that in order to move up the hill, you have to fight both the angle of the wedge and the friction force, or the friction angle. And so if we look at that, that's tightening the screw. If you're loosening the screw, then you notice that Q is going the other way. And again, like I talked about before, the friction angle is added to the wedge angle, so it's much smaller, which makes sense. It's much easier to loosen the screw than tighten the screw. Now, if you're loosening the screw and the friction angle is not great enough to escape this theta, which is what this is. So if the friction angle is less than what theta is when you add it to it, so it's not enough to exceed it, that means there's no friction, which means that the screw won't hold itself in place. It'll basically self-unwind. And so this could happen if you lubricate the screw. Generally, you don't lubricate screws because you're trying to have the highest friction possible. Anyway, I digress. So let's look at how, when I was talking about the relationship of W and the Q. So W, in the case of that's the force that's pushing down on the threads, between the threads and so as you know, as you tighten the screw, there's the force that pinches the nut to the threads in the screw itself. That would be your W. And then there's the force Q, which is what actually forces the thread to rotate around the screw. And so we can relate that to this W and this P. And we can also relate it to this block. So let's do an example, and I think it'll make more sense. But one of the things to remember is this Q times the radius, and a radius is the all little r down here. That's the same as this P times A. So that's your mechanical advantage when you're trying to tighten it. So here we have an example where we're trying to raise a car, and we have our thread. And so in order to do that, we have our threads, our moment over here. And so what we have is and this is a typical scissor jack that you'll see in a car. You'll have your left-hand threads on one side, on C and right hand, because if they're both the same threads, then you just rotate this in and out, nothing would ever change. And so this gives you a significant mechanical advantage as you're rotating it. You're able to raise up part of your car. So typical scissor jack. So let's look at what we're trying to solve. So we're given a few things. Each thread has a pitch of 2.5 millimeters and the diameter is 9 millimeters. And that should say mu sub s. Didn't change it to simple. So the friction force is 0.15. We want to determine the magnitude of the couple M that must be applied. So what couple do we need? All right. So what we'll do is, here's a drawing of that. So we know we have a 6,000 Newton force from above. We know our pitch, and I just put it in meters. And there's our pitch, our diameter, there's our friction force. We want to find our moment M. So first thing I looked at was, we need to relate the 6,000 Newton force to what's happening on the threads. So first thing I want to do is I want to relate the 6,000 to AD and CD, to CD, this should say, yeah, not AC, sorry, to CD. So that's the first. So if we do that, then what we can do is go ahead and, let's see, maybe you could be a little quicker. I'm actually going to, instead of drawing it, I can go through it just to see. So here we have AD, we have CD, we have 6,000 newtons. We know that that force triangle is created by this, by that. So we know that if we sum the forces in the y direction, we have 2 times the force CD, because remember this is 20 degrees in there, and everything's the same, 20, 20 all around. So 2 times FCD, since FCD and AD are the same, then we can determine that FCD is 8,771 newtons. All right, so that's simple. So now we know how much is in each of these bars. So then we go down to joint C and we look at that. So we know that we have FCD and we have FCE, and that is then counteracted by AC. So this is how we take the Y component and convert it to the X component. So we sum the forces in the X, 2 times FCD cosine 20 minus FAC. So now we know we have 16,485 newtons. So there's 16,485 newtons on this AC. So what does that mean? All right. So now we look at our incline. There's our block and our incline. So just like what I showed you before, we know that this side is equal to the pitch, L equals P. And we know that this whole length here is 2 pi r. All right. So now if we think about it, if we draw the diagram for the block, right? Because that's really what we're interested in right now. We know there's a force AC going down, so that's this force acting on the block. We know there's Q going to the right, and we know that there's this reaction R, right, going up this way. And so if we put those together, we know that R is going to be equal to P sub S plus theta, just like it would be on the block normally. All right. So we're really just looking right at this block. So this block represents the entire surface. And so we have it as a block that can think about the threads are a continuous surface going all the way up and around and around and around. So we just did one little piece of it. All right. Now, what we don't really know is theta, okay? Because theta is where we know there's a pitch angle, but we don't know what it is. But we can determine that, can't we? Because we were given this and we're given 2 pi r, right? So if we know that, and so if we know that, what can we say? Well, we know that then theta, that angle, because that's what we're missing, that's going to be equal to what? It's going to be equal to the inverse tangent minus 1. So, because this is theta here, right? So it's going to be P over 2 pi r. So P opposite over adjacent. So P over 2 pi r. But we know that that is equal to, actually, I don't like that, so let's say that's equal to theta is equal to inverse tangent of 2.5, and here it doesn't matter if it's because I'm keeping it the same. So 2.5 millimeters for the pitch divided by 2 pi times r, which r was 9. And so we get from that 5.05 degrees. And there we have it. So now if we go back up here, we know that this whole angle is going to be, because we had we know that that's equal to this plus this. Now, what's phi sub s? So we know that phi sub s is equal to inverse cosine of 0.15. So that's 8.531, right? Because mu static was 0.15. So we know that. So now it's just a simple relationship, right? Because we're trying to find Q. Because remember, what is the original? It says determine the moment. So we need to know Q in order to determine the moment. Now I know this is a little tricky, but what we do then is we take tangent of the Q of phi sub s plus theta, and we know that is equal to Q over the force AC, right? And that's just going Q over FAC. That's just simple right triangle. So if we do that, and we plug everything in, we plug in FAC as essentially Q is going to be equal to 485, and that's going to be times the tangent of 5.05 plus 8.531. See there? So then we get Q equals 3,983. Now we're not done yet, so we have Q. So so what does that mean? So we know, we go back to our diagram again with Q, we know it's pushing up, but we have to relate this back to a moment of rotation. So remember that the torque equals Q times R. All right. So how do we know that? Let's go back to this real quick. So you see how it's force times distance. Okay. So Q times the radius is the same as this force times distance. So this force times distance is the torque. So Q times this little radius here is going to be our torque. So that's where I get the T equals QR, okay? Now, the thing is we have two screws, we have one on each end. So we have to account for 2 times it, so times 2. So we end up with basically T equals Q, which we determined to be 3,983 newtons times 0.009. So what I did is I took the radius times 2, and that's the diameter, right? 0.009. That's what we had. We were given initially that the diameter was 9. So we end up with, and we wanted this in meters because we wanted Newton meters. So we end up with a torque of 35.8 Newton meters. So that's what it takes to rotate that. All right. Sorry, it's a little, see, yeah, 35.8. So that was a somewhat difficult problem to do. So what I would say is, that's most likely not something I would give you on the exam. I would just want to show you that because I want you to understand wedges, but I understand that's a little beyond the scope of expectation. Okay, so I think that's it. So I have gone through all of this. I would review it, but again, this whole idea of wedges, I would focus on the first problem. That's probably the fundamentals of it, and that will tell you how to deal with wedges as far as how they increase friction. So that's the end of wedges or wedges for matter. And thank you for listening. And the next lecture will be friction 4, and that'll be a short lecture talking about belt friction. And after that, so thanks for listening, and see you in office hours.